Yep. So I'm going to talk about the recap, the project that was just introduced, and recap stands for Reliable Capacity Provisioning Distributed Cloud Edge Fog Computing Applications. So today's agenda, I'm just going to go quickly through the introductions, the vision of the project itself, a few of the use cases, and our work package that we're focusing here in DCU, the simulation framework, and then I'll hand it over to Alec from Intel, and he's gonna present their involvement with their part in the process as well. So, as I said, recap has this really long name in this, so it's reliable capacity provisioning, and then enhanced remediation for distributed cloud edge fog applications. It was, as I mentioned before, it's founded by European framework for 2020, and it's was finished in 2019. So we are a consortium of partners. It's altogether 9 partners from 5 countries. If you would like to have more detailed information about the project, that's the URL you can follow to get that information. So the partners are located. Basically, we have a couple of partners in. I cannot press the button already. So here we have guys from Sweden, Tieto and Mir University. We have from UK BT, Indo and DCU from Ireland. We have 3 partners, most of them Spanish partners, and we have a German partner from the University of Ulm. So the project motivation is actually looking at the really large-scale infrastructure and the systems that can use that infrastructure. So we're looking at essentially hardware and virtualized infrastructure that is deployed on the hardware that spans over the edge, core, and remote nodes. So if you imagine the basically an infrastructure of a telecommunication systems and all the users, so basically people that live the country that uses that infrastructure, that this will be the system that we're looking at all together. And so we're looking at trade-offs from between the fog and edge, low latency, low power communication, and data center, high latency, high power. So the trade-offs between moving the data closer to the user in the edge and fog environment, and looking at the kind of what we can still need to retain in the data center further away. And we're looking on the things from the infrastructure management side, also as the application management side. So that's use the infrastructure. So the realization approach is kind of looking at the whole data, at how this infrastructure and all the applications are being used, and creating models of Notion to kind of describe this usage patterns and behaviors. So we're looking at the building models of application behavior, quality of service requirements for those applications, and a model of workflows that being created by the user. So how systems being used in general, and so we're looking to understand and predict, and then by understanding and predicting that, we're trying to enhance and remediate the usage of the thing. So that's general, again, architecture, so realization approach. We have the system here with the users and different levels of infrastructure. So edge we consider to be closest to the user, but also with the less resources, because the edge location is smaller. You cannot put really many nodes there, so you have a smaller capacity there. Then moving to core, and then cloud at the center, where cloud we consider to be unlimited resources, but it's because it's further from the user, you have lower latency of interaction. So we have in recap kind of looking at the feedback loop to build. So we have a collector, application model, workload model, learn, optimizer, and a simulator. What we're trying to do here is to collect the data analyze the data and build the models from that data, and using the orchestration remediation, elasticity and simulation to kind of orchestrate the applications and the infrastructure in there. And that's kind of for each of those components. There's small representation, or so you have the node discovery. That's the task of the recap collector. So it gathers information and kind of collates it in a form that we can use. And then we have application modeling. Based on that information, we create applications. Application models that define the behavior, and also the application model have the support for the intelligent decision making, application component placement, and auto-scaling support. Workload modeler is looking at the interactions between the users and the system, and how the user is actually uses the system. For example, in the morning, people commuting to work, and which services they access, and what's the workload being put on those services. And by understanding workload, we can improve the planning decisions, look at the quality of services we can provide, and so on. The optimizer itself, it will use the models that are being created. So once we understand the system inner workings, so we can optimize some of the system usage. So we're looking at the scaling of the components of the application, management of infrastructure, energy utilization rate, and load balancing, and so on. So, and simulation, here I will talk about more. Simulation, looking at the testing the environment, and looking at the impact and improvement that's being made for that. So the use case that we're looking, actually, so consortiums consist from kind of industrial partners, which bring use case or the problems to the project, and then other partners trying to solve those problems, working together. So the use cases we're looking at. So for example, BT looks at the NFP, so and quality service management remediation. That means looking at kind of they have an infrastructure that needs to be managed, and how to deploy the customer's cache content in a better way to serve more people and with a faster latency. Additionally, they bring kind of a specified search engine that has distributed database, and we're looking how to place those different components of the application again to have better performance and cost ratio for that. Static looks for fog computing and large scale scenarios, basically meaning they have a microservices components in their application that needs to be arranged depending on the data locations and data requests. And Tieto, they're looking at the infrastructure management, infrastructure and network management in terms of kind of providing crucial essential services priority over non-essential services. So for example, if you have an emergency situation, so they would like to prioritize the emergency services such as maybe ambulance and so on, called over the your normal user traffic. That's me. So what DCU? So DCU has the two roles in this project. So we have a dissemination. We're looking at how to spread information about the project, and work package 7. It's a large-scale simulation framework. So basically, this is the scale. To look at the scale, for example, this is one of the maps that was supplied by British Telecommunications of some of the locations that they have for potential deployments of the infrastructure. So you can see that close to the bigger cities, you have more edge locations because there are more users of the infrastructure. And within the simulation, we're looking to kind of look at the whole infrastructure, create models of that infrastructure, create models of the users, and look how the behavior, how the system behaves in certain conditions, so simulate the system behavior. So that ties in with the role of simulation and reason. So we're looking for the kind of get the idea how well our optimization and other components of the project are performing by using simulation. For example, we cannot really realistically deploy what we develop in our project into the live system because it's big and it's operational, but we're counting simulation to actually prove that the concept that we developed in the project actually works. So the optimization policies that we deployed give the benefit or more beneficial than the current system state. So we're looking at how the optimization effects will perform, and its placement, consolidation, elasticity, infrastructure, application configuration, and also cost involved. And we also obviously need to have provide value to our stakeholders or use case owners in this case, so they can say that, oh, well, actually we can use simulation in our environment and it's useful for us. Okay, I kind of maybe it's a bit too low level, but that big model that on the map, we see this devices or a lot of users that create requests, and those requests travel through network. So this is your physical layer, and this is your logical layer where the application is deployed. And we look at a lot of devices and a lot of requests traveling through the system, and depending on the type of the application demands, and we're looking at how it affects your network performance, and depending on where the application is deployed, on which tier of the network, and the response time to the users, and so on. So simulation kind of models, this is quite high level, there's more components to that, but simulation tries to simplify the system itself and make sure that all the questions that you can ask, for example, how fast will my request be processed during this workload, or where should I deploy my components in a tier 1 or metric, that should be answered by the metrics from the simulation that we're doing. This is the depiction of the network that was done with my colleague Patricia. So it's the network that we have is quite big. So those dots that you saw on the map is kind of we can also show them in the graph, and those so the black dots, I think that's the core nodes, and red is metro nodes. So it's the green ones, that's the edge nodes where they're closest to the users, and there's most of them, but they also have the lowest resource capacity on them. So we're looking at trying to simulate that magnitude of size and making sure the simulation is actually can run in a certain time, and it's has enough accuracy and enough granularity to make decisions and be useful. So the direction that we're taking two different approaches. One of them is the discrete event simulation by Cloud Sim Plus. It's an event queue simulation, so we generate every single event or what is happening in the system is kind of recorded as an event, and we have a large queue of those events, and we try to process them. By processing the events, we can determine the speed and system behavior, and then we have a timestamp simulation from another Horizon 2020 project. They're using more of the timestamp simulation approach, which is a calculation loop, essentially using the MPI-based C++ engine that is parallelize the system and produces the calculations for every second. And that's pretty much it. Thank you. I don't know, it was probably a very technical presentation. I don't know. I would be happy to answer questions. Maybe for the project itself or simulation.
Excuse my ignorance, can you explain fog computing?
What do you mean by fog computing?
Pardon?
So we look in the project itself. We look at the fog and edge computing as one in terms of location and well, basically geolocation for the user. Because in the use case that we're actually exploring, there's not much difference between them. I think some of the other academic publications or researchers, they actually distinguish edge and fog in different ways. But what we're looking in the project is the proximity to the user himself or themselves. And for us is the kind of the closest point or point of presence when the user is connecting to the network of the provider, so such as a telecom provider. That would be the fog arrangement.
So many clouds.
Sorry?
Many decentralized clouds.
Exactly, yeah. So the whole network is basically a distributed cloud, but because the actual physical locations of them, they're small, so you cannot put many resources, many racks there. You have limited capacity there. So it's greatly distributed because it's close to the user, really fast, but then you have some trade-offs to make. So we're looking at those trade-offs and how they can benefit users in different use cases.
So because you took James's slot, are you now going to take your own slot? Are you finished your own slot as well?
Yeah. So,
wow.
Yeah.
That's a record. So Alec.
Alec.
From Intel. Thank you so much.